Welcome back to this next video in which we are discussing separable polynomials over a field of characteristic 0. Okay, so in this next video what we're going to do is continue with our endeavour to understand which polynomials in the ring of polynomials over a field of characteristic 0 are actually going to be separable and which are not. And this second theorem that I'm going to give you now is actually going to tell you explicitly which polynomials are separable and therefore which are not. Okay, so here we go. Theorem 2. Okay, so I'll just underline this in another nice colour, so we'll have it in red here, a very important theorem. Okay, so here is Theorem 2 then. The polynomial p of x, so I've got some arbitrary polynomial from my ring of polynomials over the field of characteristic 0, is going to be separable over f, so I'll drop the over f, or actually no, it's wrong to drop it, so I will have the over f. P of x is separable over f, okay, if and only if, so this is a nice, beautiful equivalence, basically, okay, equivalent statements here, so P of x is separable over f if and only if we take the irreducible factorization of p of x in the ring of polynomials over the field capital F. So we know that the ring of polynomials over a field is a unique factorization domain. It's a Euclidean domain, which implies it's a principal ideal domain, which implies it's a unique factorization domain. So all polynomials in the ring of polynomials over the field capital F are going to have factorizations that are unique up to the fact that you can tinker around with which associates you're using, but that's not a big deal, into irreducibles in the ring of polynomials over the field capital F. So, p of x, we're supposing it will have one of these factorizations into irreducibles. Well, we're not supposing it will have a factorization into irreducibles here, so f1 of x times f2 of x all the way up to, and of course, I should say, to apply the condition of being separable, okay, well, to apply the adjective of being separable, you're assuming that the polynomial is a non-constant polynomial anyway. Okay, so if you go back to our definition of a separable polynomial, it's again, just like irreducible, it's an adjective that's only applied to non-constant polynomials. Okay, so indeed we know that all non-constant polynomials will have a beautiful factorization into irreducibles. Okay, so I can write p of x is equal to this factorization into irreducibles here, f1 of x, f2 of x, all the way up to, let's say, fk of x here. Okay, and here comes the condition, so you break p of x down into its irreducible factorization in the ring of polynomials over the field F, and that's important that you understand. This is a statement that you can make in the ring of polynomials over the field F. We are not going into the ring of polynomials over the splitting field for p of x, we're just working in the ring of polynomials over the field F, and the condition is that if you actually reduce your polynomial into its irreducible factorization here, these irreducibles in the irreducible factorization must all be distinct. Okay, so this is the condition. P of x will be separable if and only if all of the irreducibles in the irreducible factorization for p of x are distinct. Now, what do I mean by distinct? I mean that they are not associates of one another. Okay, one is not equal to another one times a unit. Okay, so they are all truly distinct. Right, so what I'm now going to do, of course, is prove this, but I hope you appreciate how important this is. This now gives you an utter criterion for telling whether a polynomial is separable, and of course if it isn't separable it will then be inseparable. So this tells you exactly which polynomials in the ring of polynomials over the field capital F of characteristic 0 are going to be separable and which are not. Those which have distinct factorizations, or rather factorizations into irreducibles that are all distinct, okay, i.e. you don't have an irreducible being raised to a certain power in your factorization. Okay, it's not possible to have that. They're all truly distinct irreducibles. Those are the polynomials that are going to then be separable. Okay, right. So we will start actually by proving the only if here first, because the only if is easier than the if. So we'll come back to the if. We'll start off with only if. Now, of course, only if amounts to proving this arrow here. It amounts to showing that if the polynomial p of x is separable, it implies the polynomial p of x must have a factorization into irreducibles that are all distinct. Okay, because if it is the case that this implies this, then the only way for this to be true is if this is true. Okay, because if this isn't true, this cannot be true, because if this was true, it would imply that this was true, which is a contradiction. So that's why only if means showing this arrow here, showing that if this is true, it implies this is true. Okay, so how am I going to show that this being true implies this being true? So we're starting with the assumption that the polynomial p of x is separable over f. Okay, so the way I'm going to prove that it implies this is true is just by proof by contradiction. Okay, so let's suppose that the polynomial is factorizable into its factorization into irreducibles, and you end up with two irreducibles appearing in this factorization here that are not distinct. Okay, so let's say f1 of x here and f2 of x are actually associates of one another. One is just a unit times the other, and just by tinkering around with the unit here, maybe pulling the unit out, I can turn this into f1 of x, and then I could have f1 of x to the power of 2 in my irreducible factorization here. Okay, so why then does this contradict the polynomial being separable over f? Well, of course, what you could then do is go into the splitting field. Okay, so let me just write out. We're now assuming that p of x is equal to, let's say, f1 of x squared times the rest of the irreducible factorization. So we've assumed that f1 of x and f2 of x were in fact associates if we're saying that then we're going to not have all of these irreducibles distinct. Okay, we've pulled the unit out of f2 of x, say we've swallowed it into one of the other irreducibles over here, and we've turned it into f1 of x. So we've now got f1 of x squared, and then the rest of the irreducible factorization will be here. But of course, what you can now do is you can now go up to the splitting field for this polynomial p of x, this field extension of f, which is the splitting field. So let's say that k is going to denote the splitting field, which is a field extension of f, over which this polynomial completely splits down into a product of linear factors. Now, when you actually want to split this down into linear factors, of course all you're going to do is split all of the irreducible factors in the ring of polynomials over the field f into linear factors. So what you then do is have a statement in the ring of polynomials of the splitting field, and all of these irreducibles would now split into linear factors. But the problem is here we've got f1 of x squared, so f1 of x will split down into not irreducible factors, linear factors in the ring of polynomials over the field capital K. But now you're going to get all of those linear factors squared, so that means that all of the roots pertaining to those linear factors are not going to be simple roots. They're going to have multiplicity at the very least 2. Okay, so they're going to be repeated roots, which then contradicts the polynomial being separable. Okay, so if it's the case that you have in your factorization into irreducibles, two irreducibles that are not distinct, they're associates of one another, then in the splitting field this polynomial is going to have roots that are not simple, roots that at the very least have multiplicity 2. Okay, and that's obviously contradicting the polynomial being separable. So if the polynomial is separable, it implies that the factorization of this polynomial into irreducibles in the ring of polynomials over the field f gives all irreducibles that are distinct. Okay, so that's the easy one. Now let's do the more difficult one, the if here, but it's still not that difficult, it's just slightly more difficult than that one. Okay, so we now want to prove that if it's true that our polynomial p of x has a factorization into irreducibles over the field f, where all of the irreducibles in this factorization are distinct, then it's good enough, it's a good enough criterion for it being the case that p of x is separable over f, and therefore these two statements are truly equivalent to one another. So let me put this here. Now we're going to approach this in a similar way to how we proved only if there. We're going to do it by proof by contradiction. Okay, so we're going to assume obviously that this is true. That's our starting assumption. So we're saying now that we've got this polynomial p of x, which if you take its irreducible factorization will have all distinct irreducibles, okay, in that irreducible factorization. We're now going to assume the opposite of what we want to prove. We're going to assume that p of x is not separable, it's inseparable over f. And therefore, what we're going to need to do is we're going to arrive at a contradiction. We're going to show that with that we can disprove this. We can disprove all of the irreducibles in the irreducible factorization being distinct. Okay, so let's do this. So remember, p of x we're assuming is a non-constant polynomial. You can't apply the adjective of separable over f to a constant polynomial. So we are assuming p of x is a non-constant polynomial. So we've got f1 of x times f2 of x all the way up to fn of x here. And we're starting with the assumption that all of these are distinct. Now, if we then assume that p of x is inseparable over f, then what does that mean? That means that if you go to the splitting field for this polynomial over f, then p of x must have in that splitting field a non-simple root, a root with multiplicity not equal to 1. Let's call that root alpha. So let's say alpha is an element of k, and alpha is going to be a multiple root of p of x, a root that has multiplicity greater than 1 over the splitting field capital K. Okay, now what we want to do is arrive at a contradiction for these two, arrive at a contradiction for these irreducibles here all being distinct in the irreducible factorization. Now, if alpha is a repeated root, then that must mean that when we actually go into the ring of polynomials over the splitting field capital K, and of course split all of these irreducibles down into their factors in terms of linear factors, then we must have the linear factor x minus alpha appearing more than once. Okay, so understand what I'm doing here. We have our factorization of p of x into irreducibles here. That's a statement in the ring of polynomials over the field capital F, but we're now going to upgrade. We're going to go into the ring of polynomials over the splitting field capital K, and what we'll be able to do there is split all of these irreducibles down into products of linear factors. And what I'm now saying is if we've got this repeated root, then x minus alpha must appear at least twice in this great big factorization into linear factors that you're forming here. Now we know from Theorem 1 that all irreducible polynomials are separable, and that means that in the splitting field they are not going to have repeated roots. So what I can say is that when you take, for instance, f1 of x here, which is an irreducible polynomial, because we know all of these are irreducibles, they're the irreducible factorization. Okay, when you take f1 of x and split it down into its linear factors over the splitting field capital K, you are not going to get x minus alpha appearing more than once, okay, if once at all. Okay, so in all of the bits contributed by each of these irreducible factors, you're not going to get x minus alpha repeated. So the only option is that in different factorizations into linear factors for these irreducible factors, you get x minus alpha appearing. Okay, so what I'm saying is you might get x minus alpha appearing here only once, but you might also get it appearing here. That's the only way that in this factorization for p of x over the splitting field K into linear factors that we can get x minus alpha appearing more than once. It cannot come more than once just by splitting these irreducibles. It has to be the case that it appears in the factorization into linear factors for more than one of these irreducible factors. Okay, so what I can now conclude then is that for at least two of these irreducible factors, alpha is a root of them. Okay, so let's say just arbitrarily that it's f1 of x and f2 of x. And so what I can now say is that f1 of alpha is equal to 0 and f2 of alpha is equal to 0. That's the only way. You must have two of these irreducible factors which both have alpha as a root. It cannot be the case that just one of these has alpha as a multiple root, because we know that all irreducible polynomials are separable. That was Theorem 1. Okay, so now we know that we have these two irreducible factors which have alpha as a root. Now, of course, because we've got polynomials here that are non-zero with alpha as a root, we know that alpha is algebraic over f. And what do we know about algebraic elements over f? we know that they will have a minimal polynomial over F that will be an element of the ring of polynomials over F. And we also know that all other polynomials in the ring of polynomials over the field capital F are going to be in the principal ideal generated by the minimal polynomial for alpha over F. Okay, so what I can now conclude is that the polynomial f1 of x and the polynomial f2 of x are both elements of the principal ideal generated by the minimal polynomial for alpha over F. Okay, i.e. they're both multiples of the minimal polynomial for alpha over F. Okay, now, we also know that they are irreducible. Now, the only irreducible polynomials in this principal ideal generated by the minimal polynomial for alpha over F are the ones of the same degree as the minimal polynomial for alpha over F, because anything that's got higher degree than it, that's going to be a multiple of the minimal polynomial of alpha over F. It's going to be a product of the minimal polynomial for alpha over F times a non-unit element. Okay, so it's not going to be irreducible. So the only irreducible polynomials in here are the things of the form a constant polynomial, i.e. a unit, times the minimal polynomial for alpha over F. So because both of these are irreducibles, they're just both going to have to be units times the minimal polynomial for alpha over F. So what I'm saying here is that f1 of x is going to have to be some constant polynomial when I just call it c1 times this minimal polynomial. Now this huge name for the minimal polynomial for alpha over F is getting in the way here, and similarly for f2 of x it's going to have to be some constant polynomial c2 times the minimal polynomial for alpha over F. Okay, but of course that means that, you know, just because all constant polynomials except the zero polynomial, which this isn't, are units, we can invert this. So we can say the minimal polynomial for alpha over F is going to be equal to f1 of x times the multiplicative inverse of c1. So just a bit of algebra here. Okay, and then substitute in this expression now in here, and of course what you'll end up with is f2 of x is equal to c2 over c1 times f1 of x, i.e. that they are related by a unit. Okay, so they are associates. So I've now proven that f1 of x and f2 of x are associates. Okay, so overall, just to summarize the argument again, we said that if it was the case that p of x was not separable, if it was inseparable, then it would have a multiple root. We called that alpha. Okay, when we actually take p of x into the ring of polynomials over the splitting field K and split it down into its factorization in terms of linear factors, what that corresponds to doing is splitting all of these irreducible factors in the ring of polynomials over the field F into their factorizations in terms of linear factors. Okay, we know that if alpha is a repeated root, x minus alpha must appear overall in this great big product twice, or maybe even more, but at least twice. And we know because of Theorem 1 that it cannot appear more than once in the irreducible factorizations into linear factors for a single irreducible factor here. Okay, so that meant it had to appear in the factorization into linear factors for at least two of these irreducible factors here. So that would mean these irreducible factors had alpha as a root. So f1 of alpha was equal to 0 and f2 of alpha was equal to 0. Alpha is algebraic over f, clearly, so we know that all polynomials in the ring of polynomials over the field capital F must be in the principal ideal generated by the minimal polynomial for alpha over f, the unique monic irreducible polynomial which has alpha as a root in the ring of polynomials over the field capital F. But the only irreducible polynomials in here are those that are just constant polynomials times this, because anything else is a non-constant polynomial, i.e. a non-unit, times this minimal polynomial, which of course we know is not going to be a unit. Okay, it must be degree 1 or greater. Okay, so that then allows us to say that each of these must just be some constant polynomial, a unit times the minimal polynomial, and of course that then allows us to conclude that these two are related by a unit and that therefore they are associates of one another, contradicting all of these irreducible factors being distinct. So indeed, if we assume that the polynomial p of x is inseparable, it contradicts all of these irreducible factors in the ring of polynomials over the field F being distinct, and therefore we have proven the theorem it must be the case that if this is true, then this is true. Okay, so we now have fully characterized which polynomials are separable over f. Okay, it is those polynomials which, when you split them down into their irreducible factorization in the ring of polynomials over the field f, have all distinct irreducible factors. And I must state, because I missed it out in that final line, that we are talking about fields of characteristic 0, not general fields. So this works for the rationals, the reals, the complex numbers, and any other field that you've got that is characteristic 0, but not for those fields which have characteristic equal to a prime natural number. Okay, and with that we will end this video.